Okay, so let's start our lecture today. Uh, so last time I think I constructed a universal covering map. Okay, and then I'm trying to specify the starting point, endpoints. So here I'm letting so that is X tilde to be the universal covering map. And since this gamma is a subgroup of the pi 1 XX naught, that's also being identified with the deck transformation group, right? So, yes. Okay, so here I let this gamma to be the I like gamma to be the universal covering map, and then that this group gamma to be the deck transformation, and then therefore I can create a covering quotient space, which is also a covering event surface. Okay. Okay, so now I want to use the okay, so I want to use the corollary 5.1.4, which says that if you have oh wait, okay. Okay, so I think the theorem 5.1.6. So remember here, okay. So here we have these two as our okay, so by the theorem 5.1.7, yeah. So theorem 5.1.7 says, if I have if X tilde is a semi-connected covering connected Riemann surface, and then this group gamma is a subgroup of the group of automorphism that acts probably discontinuously and freely on this X tilde, and then you let this map to be the corresponding quotient space mapping, and then we have that there is a so first there is a unique holomorphic structure X with respect to wait, hold on. Yeah, so okay, so here they use a different gamma. So here, okay, so just ignore so the first part is about, so here, okay, so, wait, hold on. Yeah, so the first part is about the holomorphic structure of this space, but we are in the construction of the theorem 5.1.7, this X is constructed to be the quotient space by the so in the theorem 5.1.7 there is also a group gamma that this space X is actually constructed by the quotient space of this semi-connected Riemann surface. But in our scenario, we already constructed x tilde so that this x tilde is the unique universal covering space of this X. Okay. So we don't need to worry. We don't need to really worry about the gamma. So okay. So where the and I think there is a So I think there is an identification between the Dirac transformation. So the Dirac transformation is so the Dirac transformation group is actually a subgroup of the group of the automorphism group of X tilde. So this is by the holomorphic lifting theorem. Okay. Yes. So wait. Let me be more careful here. So. Then shoot. Okay, so. Okay, so let me go to the construction of this gamma. Okay, so actually, is there any way to show that X tilde is a corresponding quotient space mapping? Then we have the following. Gamma be a subgroup of the automorphism group.
have a commutative diagram.
Okay, so so you think of this one as your first gamma.
Okay. So and then you think of
Okay, so yeah, so sorry, in the color 5.1.8 there is a gamma. So okay, so you think of so here you think of the gamma as a subgroup of the Dirac transformation group of this gamma, and then
I think here what's going on here is that this x
yeah, so I think the question is that we constructed this x by, so we constructed this x tilde by the
existence of useful covariance. So in the theorem 5.1.7 where this x is actually given by the so the theorem 5.1.7 we start with this x tilde, right? And then we fix any subgroup of the automorphism group X, then X properly discontinuously and freely on this X tilde. Okay.
So we fix this one to be our
subgroup. And then
so the thing is that
okay, so is it true that
okay, so is it true that this gamma, which is created by the uniqueness of the holomorphic, uniqueness of the universal covariance, is exactly the same thing as
the quotient map?
quotient by the action of that transformation group of gamma. Okay. Oh.
Okay, let's see. So
okay, so what is the definition of this gamma? So okay, so this x tilde
is being defined as Okay, so this X tilde is being defined as the space P mod out the equivalence relation. So where this P is the set of paths from 0, 1 to X, such that it has initial point X naught. Okay, so we fix the point X naught. So fix. And then this equivalence relation, so okay, so alpha is equivalent to beta if and only if there has homotopic. To each other. Okay. Okay. And then this gamma. Okay. This gamma of let's say equivalence curve alpha is equal to just the alpha at the endpoint, right? Okay. Okay, so quotient, the deck transformation group. Let me think. Okay, so there is a unique identification with the deck transformation group of the pi 1 x naught, right? Where okay, so I think it's really not that. So yeah, so you can definitely construct a quotient map. You can define the quotient map and then okay. Okay, let's see. So if x in x tilde. Okay, so I'm looking at the identification. So okay, so basically the theorem says, okay, so I'm looking at the theorem that's telling us the equivalent relation of these two. So if you have a x in x tilde
if you fix a point x in this x tutor, and then
okay, shoot.
okay, so here we fix the point x naught in this x, okay, and then pick a point x naught tilde that is belongs to the so this is the universal covering, okay, so gamma inverse of gamma inverse of x. Okay, so what is so how is this pi 1 of x naught being identified with the Deck transformation group?
So basically, you pick any x in this x tilde,
and then let
small gamma tilde be a path because it's simply connected. Yes.
so
Okay. So
be a path from x naught tilde. So x naught tilde is like the base point. Okay. So from x naught tilde to x.
and then okay.
And then you let
Element alpha be in pi 1 x naught. Okay.
base at x naught be an element pi 1
Of x naught.
Yeah, so you think of this one as a base one, and then loop alpha.
And then okay. Oh, okay.
And then you let this alpha tilde be the
lifting.
Actually, let me see whether you can see that. Yes. Okay. Yeah.
And alpha tilde is a unique lifting of alpha.
Okay.
Of alpha to a path. Okay. To a path in
X tilde
with
the base point
being equal to x naught.
Okay. Yeah, so there is a unique lift. Let's say alpha tilde. Okay.
So
Okay, so now you get, so here there's another map. So okay, so here for this one x, okay, so there is a map. There's a path gamma tilde that joins the x naught to x. Okay. So
now okay, so now now that
okay, so now that
gamma tilde 1 be the unique lifting of
gamma, small gamma, which is equal to the projection of this gamma tilde. Okay. So this is gamma tilde, and then you project it down. Okay. So you may get a point. Maybe I draw it here. X. Okay, so this is gamma. And then wait. Unique lifting. If you plug in x, okay.
okay, it's in unique lifting of this gamma to a path. To a path with
Okay.
so with the initial point small gamma tilde 1 of small gamma tilde 1 of 0, the initial point being equal to the
Alpha tilde 1. Yeah, so here you need to take a path that start from here. Okay. So, okay. And then this point is like, okay, so then this inverse mapping, right? So I define like, so that sigma be the inverse mapping. Isomorphism. Okay. So then we have the relation sigma of this alpha right, so here we have this alpha, okay. So sigma of this alpha based at x naught, which is equal to,
1 + 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2
Okay, so this is a deck transformation. Okay, so this is a deck transformation. So this refers to a deck transformation group of X is actually equal to okay, so this lifting gamma tutor of 1. Okay, so basically this point. Okay. So okay. Wait, why is that helpful? Let me think. Oh, okay. So wait. So why is it true? So when you quotient by the action of deck transformation, so namely what you do is that, yeah. So namely what you do is that you are taking this pi 1, right? So basically for each deck for each action there is, I think that, yeah, so for each action there is like this you kind of it's kind of like you put, oh, okay, so for each action, yeah, so for each action it's the same thing as, so for each action there is the same thing as yes, so there is the same thing as there is a corresponding yeah, so there is a corresponding alphas, right? Such that this is true, right? So this is true, okay. So for each action, yeah. So wait. So for this quotient map, so why they are the same map? Okay, so why they are the same? So here you are quotient by the action of deck transformation group. So your quotient, yeah, what does that really mean? So here for this quotient map, right? So for this quotient map, so you are taking So for any element, right? So the element in this executor are exactly the homotopy class, right? Yes. So if you take any homotopy class, so what does this map send you? So it will send you to another homotopy class, right? So what is the homotopy class that I send you? So okay, so let's call this okay, so let's call this equivalence class by the gamma. Okay, so alpha is, so here a homotopy class of alpha is equivalent to a homotopy class of beta if and only if okay, so if and only if there exists a small, let's say, okay, so maybe I'll use different letter, like phi in this deck transformation group of gamma, such that okay, this alpha is equal to, or let's say it's beta, or same thing, yeah, phi of alpha, right? Okay, so what does that mean, right? Okay, so that means I think I'm running out of space. So so this means, so if this implies, okay, so because for each element of the deck transformation group gamma, there is a unique element in this pi 1 that such that, okay, so this implies that there is a unique okay, so this implies there is a unique what's the name? Let's use the letter L. Okay, unique L in the pi 1 of x. Hold on 1 second. Okay, so pi 1 x naught. Okay, and then such that okay, so yeah, maybe I'll use this one. Okay, close class x naught, such that you have that. Okay. Is equal to okay. Okay, so what does that mean, right? So what does that mean? Okay, so this means that okay, so this means that fees of this means that fees of alpha, which is equal to this phi of or sigma of Lx naught okay. Okay. So of this alpha. Okay. So what does that mean? Okay. Which is equal to okay, so here you think of this x. You think of this x as this alpha. Okay. And yeah, so this x naught, they are the you think of the x naught are the elements are the pi 1 x naught. The wait. Okay. So what is okay, so okay, so I think I'll just pause today. Okay, so my goal is to basically show that. Okay, so namely, I want to show that the space that's constructed by the quotient space mapping is the same thing as the original construction of universal current space of X from the scratch. Okay, I want to show that they're the same, so therefore I can apply the theorem. Wait, is there any theorem that already tells you? Oh, shoot. Okay. 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 Okay, so I think these two spaces, they are homomorphic to each other. Okay, so they are homomorphic to each other. So act properly, discontinuous and free on this size to that. Yeah, so they are homomorphic. Okay, so I'll continue next time. Okay, I'll continue next time.